Name is Will Buchanan, and this is my Lab 5, which will be looking into the falling slinky. So when you drop a slinky, something pretty weird happens in that the bottom part of the slinky right here doesn't seem to move at all. It's just suspends in the air. And that doesn't look very normal. It kind of looks like it's just stuck there. So in this lab, the floating slinky will be explored and will be modeled both experimentally and computationally and hopefully explained. So there are two main forces concerned with the slinky here involving the spring force and the gravity force. And when you consider the top of the slinky, the spring force is pulling inward towards the center of the slinky, and the gravity force is also pulling downwards. However, at the bottom of the slinky, the spring force is pulling upwards and the gravity force is pulling downwards. And these two forces offsetting each other is what causes the bottom of the slinky to seemingly not move at all after the slinky is released. So here we see the gravity force is equal to the mass times Earth's gravitational force, which is 9.8 meters per second squared. And this J hat is basically saying that this gravity force only acts in the y direction. And then concerning the spring force, it's equal to the spring constant multiplied by the distance the spring is from its rest length. And then these forces are unequal or don't balance out each other to a net force of 0, acceleration will occur, which is what happens at the top of the slinky. However, at the bottom of the slinky, the spring force pulls up and the gravity force pulls downward, and these forces cancel out. So for the conditions and setup, the system will be the Earth and the spring, and the setup is a slinky recorded in slow motion that has been held in the air from the top coil up here and then released down. For the experimental component, tracker was used to collect accurate data of each position in the frame. And this guy's height right here was used for distance calibration because I knew he was 1.75 meters tall. The mass of the slinky is 0.25 kilograms. The initial position of the bottom of the slinky was 0.5 meters in the X direction and Y direction. And we use right here, his right foot for the origin. And the initial velocity was 0 because the slinky begins at rest. And now let's see the tracker in action. So we can see the auto tracker here is focusing in on the bottom of the slinky. And we see that in the Y direction, the bottom of the slinky is not really moving at all. And we also see auto tracker picking up the top of the slinky as well. And that bottom half of the slinky just stays put until the top of the slinky finally reaches it, and then the entire slinky falls down to the bottom. You see each frame being recorded down here on the bottom right. And then the results, this is the top of the slinky, and it's as expected, it falls in a very normal pattern. However, we see the bottom of the slinky does not even move a bit until the top of the slinky reaches it, which is what we also saw in the video. And then this is just the bottom half of the slinky. Again, it does not really move until the top half reaches it. And then for the computational model, the initial conditions were 0.25 kilograms for the mass of the ball. And we see our initial position again, the Earth gravity component and the J hat direction vector. And then for the computational model, it was pretty difficult to actually replicate a spring. So instead, two different while loops were used, one to model before the top half of the slinky reaches the bottom part of the slinky, and then after the two parts of the slinky meet each other. So this is the while loop before. It's pretty much just has the slinky not moving at all because the spring force and gravity force are equal to each other. So there's no motion. And then in this while loop, which occurs after 0.7 seconds, or when the top half meets the bottom half, we see that it's just going to have acceleration downwards due to gravity at this point. And then this was the computational model versus the experimental model. We see that auto tracker jumped around a little, where the computational model is much smoother. The computational model also better shows that the slinky is accelerating downwards and increasing in velocity. And again, a much smoother path due to auto tracker sometimes jumping around. And the computational model can definitely be improved going forward. The top of the spring could be added to the model, and then an actual spring force could be added into the code rather than just two while loops to split things up. And that's it for my lab. Thank you for watching.